Now we're going to look at 2's complement on the number circle. So 2's complement, we still have our leftmost bit represents our sign, meaning that if it's a 0, it's a positive number. So we still get this divide across our number circle of positive and negative numbers. Here's our positive numbers and here's our negative numbers. So that means that we still can go about here in these least significant three. Well, what happened? Our least significant three bits here represent our magnitude for our positive ones directly, right? They directly represent the magnitude, and there's no fancy footwork we have to do. So this is a 0, 1, 2, 3, 4, 5, 6, and 7. Now, what I like to do is, especially because 2's complement is a little bit more complex, it's not super complex, but what I like to do is do a couple test numbers and see where they land on this negative side. So let's figure out what -1 is. So my procedure is always I'll go to black. Add 1. Oops, not add 1. We want to flip bits. Then add 1. The stupid way I remember this is it's like the Facebook A1 steak sauce. Like, I don't know, it's stupid, but I have FB A1, whatever. Okay, so we're gonna. This represents +1, right? So we want to get -1. We flip the bits. And then we mathematically add 1 to this. We end up with 1, 1, 1, 1. So this is -1. So we got our -1 right here. Now let's not just assume that this is -2. Let's verify it, right? If you want to verify it, we could do it two ways. We could see if this turns out to be 2 if we negate it, or we could go from +2 to -2. So let's go from +2 and see if it gets us this sequence. So we're going to, once again, flip the bits and add 1. So we're going to flip the bits here. That leaves us with 1, 1, 0, 1. And if we add 1, and here I'll draw it really tiny here. We're going to add 1. 1 and a 1 is a 0. With a carry. 1 and a 0 is a 1, and then 1, 1. So sure enough, it looks like this is our -2, and we can assume that our sequence goes the rest of the way here. Except, is it true for this last sequence here? Because that would mean this is -8. And we don't have a +8, but is this -8? Well, let's go the other way. Let's convert this to a positive number. So if we're going to flip bits and add 1. So if we flip the bits here, we get 0, 1, 1, 1. And if we add 1 to this sequence, well, if we increment 0, 1, 1, 1, we end up with 1, 0, 0, 0. So we end up with what we started with, which is pretty crazy. And so is this -8? Like, is that what this is? Is this a value of 8? Or a magnitude of 8? Well, to kind of solidify this argument that this represents a magnitude of 8, in this case it's -8, let's actually expand this to 5 bits. So -8 in 5 bits, right? We would have, a +8 in 5 bits would be 0, 0, 1, 1, 1. And if we add 1 to this, right, if we add 1, what we would get, well, let's just do it, add 1, is 0, 1, 0, 0, 0. And that's a magnitude of 8. So this is can potentially be a little bit confusing, but it's this is -8 there. So now let's see if we've got our values. Do we have a single 0? Well, it turns out, yes, we do. Actually, hold up. Real quick, just to further solidify and make sure that this is not 0. Let's take the 2's complement of 0. So the 2's complement of 0, 0, 0, 0. So we're going to flip our bits. And then we're going to add 1. If we add 1 to this, it's going to roll over to zeros. So a -0 just comes right back to 0. So that makes me even more confident this is -8. But either way, our properties here, do we have a single 0? Well, yes, we've only got 1 right there. Do we have a clean 0? Yes, our 0 is represented by only 0, 0, 0, 0. Do we have a unidirectional increase? Well, let's start at our minimum here, -8, -7, so we are increasing, -6, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7. So as we go around the circle, it is a increase of 1 unit, right? We're increasing by 1 unit around the whole circle. Besides for this rollover point, but you're always going to have that. So we'll say yes. Do we have a clean rollover? Is the minimum right next to the maximum? Well, our minimum is -8 and our max is 7, and they are right next to each other. And the last thing is, do we have a full range of values here? Well, yes, because we've got that -8 there. That means we don't have 2 zeros, and each binary sequence represents a unique quantity. So do we have a full range? Yes. And that's why 2's complement makes us happy, because it's got all of the properties we want, right? We got a big smiley face for 2's complement. That said, it's not as easy to interpret, right? If I say here's a number, if I say what's the magnitude of this, it's not that simple, right? We can't just look at it and say, oh, this is, oh, well, I don't know, because we'd have to get the magnitude of this negative number, right? We know it's negative because of the sign bit here. We'd have to flip the bits and add 1. So I guess let's just do it real quick. Just for completeness, we're going to flip our bits. So that leaves us with 0, 1, 0, 0, 1, 0. Oh no! Okay. And now we're going to add 1. So 1, 0, 1, 1, 0, 1. So what is our magnitude here? Oops. I just flipped the bits. What am I doing? We're adding 1. Sorry. So that leaves us with 0, 1, 0, 0, 1, 1. So this is 16, 17, 18, 19. So just looking at this and saying, what's the magnitude? You can't easily do it. You can't just look at this and say, oh, that's a -19. So that's the downfall with 2's complement. But luckily, humans don't often have to be looking at this, right? It's going to be computers that are dealing with this, and they don't really care if it's easy or hard to read, just as long as it's easy to do math with and it takes up less hardware.